speak today about modern ground solar minimum and terrestrial cooling. And this is the part which you can also find on my personal website, shown here, and the number of publications. The work was done in collaboration with Dr. Simon Shepard, who worked for Bradford University, retired now, Elena Popova from Moscow University, and Sergei Zharkova from Hull University, with my thanks to material for this talk. Oops. So the contents, my talk will be, I will introduce you to current index of solar activity, then we move to the new proxy we proposed to use and show that with this proxy we managed to understand appearance of ground solar minimum and describe the parameters of ground solar minimum in the past, like Maunder, and then the ground solar minimum, which we observe already now and will be observing the next 30 years. So what is this SON and why the solar activity is described? How? It's been described with this help of sunspots. This is what you see on the sun without any instruments, large sunspots. You can see if you project the sun on the wall, you see the spots on the wall, and in the past, without instruments, people did manual drawings and measured number of sunspots which appear on the solar surface. So the sun is yellow, the sunspots are dark, and what happened, the sunspots, like walking along the 11-year cycle, and they migrate from the middle latitude toward the equator. And in 18th century, Wolf introduced solar activity index, average sunspot numbers, which we use until now. The bottom line in this plot shows you the average monthly daily sunspot areas in the total number, in the total area of the sun. And it will show that this area actually changes every 11 years. If you can see, it varies between 10 to 12, but average duration of the solar activity is about 11 years. So you see some particular cycles of 11 years can have rather large number of sunspots, like in 1960, for example, in here, and then in 2010, we had large number of sunspots. Therefore, this solar activity index was used for the past probably 200 years, maybe even longer, given that Chinese astronomers observed sunspots up to a few hundred years before. So this is quite established solar activity index. On the top plot, there are so-called butterfly diagrams, which show you position of the sunspots at the beginning of the cycle, marked with the vertical line, and the migration toward the equator toward the end of the cycle. So you see, they clearly show that toward the 20th century, we had large number of sunspots. The intensity area of the sunspot was much larger, which even was called modern solar maximum. So this is fine and been established. The problem is with this, how to explain what will happen soon, what will happen not only tomorrow, what will happen in 10 years, in 20 years, in 100 years. So the sunspot occurrence or change of the solar activity occurs because the sunspots are moving on the surface. The reason to look at this sunspot was to look who are these guys, what they do, and turn out the sunspots, these are places where large magnetic loops are embedded into the solar atmosphere. So basically, the sunspots are measured actually location of magnetic loops on the sun. So despite the solar activity index is a scalar magnitude of area of sunspots on given days, it turned out that they have magnetic field, and the magnetic field of the sunspot which is closer to equator, which is called leading polarity, and magnetic field which further from the equator, the sunspot group is called trailing polarity. And therefore it turned out that basically the area changes because the magnitude of magnetic field is changes. This is what people decided, that it turned out that sunspots reflect actually the change, the magnetic field of sunspots, because it is 1,000 times greater than surrounding area. It is very good seen, and the magnetic field is easily measured. So the first magnetic field measurements were exactly from the sunspots, but they go in pairs, and always having opposite polarities, and all sunspots of the same hemisphere have the same magnetic configuration. So later in 1955, Parker found that change of magnetic or change of number of sunspots actually is related to the work of the solar dynamo. It's variation, electromagnetic force, which is changing inside the solar interior and produces the dipole. Like on the left-hand side, you have dipole with the south pole on the bottom and the north pole on the north. And this is during the minimum activity. There's no sunspots, but polarity are strictly separated. Northern polarity is north, southern polarity south. But then over the time, the sun rotates, and because sun rotates not equally, it rotates like a gas, so it rotates faster on the equator and slower toward the pole. Therefore, sunspots and these magnetic loops, they become twisted, they become put around the other two, they twisted and leaned and so on, and they make the magnetic field to migrate. So the southern polarity magnetic field shown in the center during the maximum of solar activity migrates toward the north, and northern polarity migrates toward the south. So this is when we have maximum solar activity. And eventually when you arrive to the minimum of the next cycle between two cycles of solar activity, what you can see that boom, your north pole having southern polarity and your southern pole having northern polarity. So polarity is changed. It changed not only in the sun spots, it changed in the background field, obviously, because as you've seen, the sunspots are those magnetic loops which are embedded into the like water background magnetic field. And it is much smaller, but it still does exist, and it needs to be treated and considered how it affects the variation of this sunspot. Is it role of this background magnetic field? How big is sunspot, or how long it does exist on the surface? So in 2008, Zharkova et al., they done investigation of comparison solar background magnetic field and sunspot magnetic field, because we had solar feature catalogs. We had all data digitized. So the top is background magnetic field, if you look at this plot, and the bottom is the sunspot magnetic field. And you can see the blue is northern polarity, and the orange is southern polarity. You can see that actually the polarity of background magnetic field is always opposite to the polarity of leading sunspots. So what we found, very strong correlation between polarities and occurrences of sunspots, and what it gave indication that possibly the solar background magnetic field is actually the main guy which defines where exactly sunspot occur, with what strength, and how it imposes the solar activity we observe. So after that, we decided to look at the solar magnetic field of the whole sun. But it is as a white light, as I shown this on the top. It has many, many different waves, and it was very difficult to understand all this magnetic field on the surface. Therefore, we decided to use a little bit trick, like this prism, glass prism acting on the white light and producing the waves of different colors, of different wavelengths shown here. So we needed to find this prism to separate magnetic waves on the sun. And this prism for magnetic field was actually principal component analysis. So if you had all magnetic field data, magnetic field magnitudes in each pixels in 1024 pixels by 1024 of the whole solar disk, you apply principal component analysis and you can obtain components of principal components and other independent components of contributing to this particular field. So this is what we run. We run principal component analysis of magnetic field. We obtain 3 diagrams which show us the eigenvalues, or if we rephrase it with the wavelengths of the magnetic waves created on the surface. And what we discovered, actually it is principal components showing us that these waves come in pairs. You see the first two pairs, and later we shown they were assigned to the dipole magnetic field, which is shown on the first image. Then we have another pair in here, which is assigned to quadruple magnetic sources. And then you can use sextuple sources, octuple, and so on. After 5% of variance, we probably the other sources, but we can ignore them for the observational part. Our resolution is not high enough. So what, applying this principal component analysis, we managed to resolve now 2 principal components, 2 waves on the solar surface. And this is on this, if we use the data cycle 21, 22, 23 of full disk magnetograms of Wilcox Solar Observatory. And we obtained these principal components shown by the red line and the blue line. Red line is northern polarity, blue line is southern polarity. What we discovered, you see the vertical dashed line show you separation of the cycles. So for time being, we don't look at the right-hand side, only 3 first cycles. What we found that these waves look somehow organized. So it doesn't matter that cycle 21, both waves, they start in opposite hemispheres, about middle latitude on the sun, but they both move towards the same hemisphere, and then they meet. They move, in this case, in cycle 21 and cycle 23, this wave moved to the northern hemisphere, and around the time when they meet, we have the maximum solar activity, and then after that, the wave keep going, and the southern polarity, they keep going to the southern hemisphere, and in the cycle 22, the 2 waves, the maximum achieved in the southern hemisphere, so southern hemisphere become more active, and so on. So this was nice. You obtain this. It is the data obtained digitally with computer science, principal component analysis. But what is interesting, how we can obtain the other data? Our task was to classify, to obtain the data that we can basically predict, expand our curves to the future. So we managed to expand, but what we did run, we needed to run symbolic regression analysis on the data. So the previous data were purely observationals. We didn't do any, we did a little bit filtering and cleaning, but then we wanted to have expressions of the data in terms of some known periodic functions, because dynamo models, they always give you some periodic function describing waves generated by sun inside the interior. So we wanted to reproduce this with the formula, and it turned out that when you take the full magnetic field, this method doesn't work. We couldn't get any reproduction. But on the principal components, when you manage to separate magnetic field into dipole magnetic field, like we did, 2 components for the dipole magnetic field, we managed to express each component through this series of 5 terms, when all the coefficients are known and the frequencies are known. So it will be product of 2 cosine, and when the what is most important, that cosine by cosine, it's very difficult to guess that it will be such a different shape, and the phase of the wave also is a cosine function. So this came as a full surprise for us. We got these 2 components, we got all these numbers, and then we come back to this picture. We managed to reproduce, this is what was the dashed line. This is the measurement we got. This is the period about 5 years while we were developing principal component analysis, developing this classification. By that time, sun kept moving and developed new, we had new data. So we could compare, this is where we started, vertical line, and these aligns with dashed and solid line, where we can compare our curve, which we derived, with the formula which we derived. So the formula is given by solid line, the curve produced by formula given by solid line, and the data obtained straight from the magnetic field is dashed line. As you see, the accuracy pretty close. So obviously, when you have clean wave, you can nicely reproduce it by formula. So what we now can produce these principal components for cycle 24. At that time, we went the cycle 24, and now cycle 25, and then next cycle 26. What occurred to us strange, what you also see, obviously, that these waves, despite they were meeting, they should meet each other to get the maximum solar activity. What happened in cycle 25, as you see, one wave goes to northern hemisphere, another goes to southern, and they meet nearly at the end of the cycle, and the very low height above the equator. And then they move again in the cycle 26 in the opposite hemisphere and nearly meet at the equator, and which gives you the signal that probably the solar activity will be reducing because the waves do not interfere with each other. So we wanted to reproduce this summary curve of these 2 PCs, and it shows indeed that it was solar activity cycle 21 pretty high, then reducing in cycle 22, reducing, and obviously we see the cycle 25 and 26, it reduced very dramatically by 60–70% compared with the previous cycles. So we got these nice results. We wanted to understand, what do they mean with this in comparison with the standard solar activity index? So what we did, we basically reproduced this summary curve to the positive axis. So instead of using magnetic field, southern and northern polarity plus and minus, we put, forget about polarity, reproduce this curve back to the positive, produce modulus summary curve, and compare it with average sunspot number. So this is, dark line is our modulus curve, and red data. These are real data, average sunspot number, which we took from the catalog. And as you can see nicely, that this modulus summary curve reproduces pretty nicely our solar activity index. It seems so nicely, apart from the cycle 23, when we had slightly smaller magnitude than they produced, but then they came up, it was an error in classification. They needed to reduce this one, but we didn't know about the error. We seen the difference. It was strange to us, but the astronomer observers, they found the discrepancy, they found the error. So this gave us an indication that voila, we got a new solar activity index, which defines not only area of sunspots, but what we have advantage in our index, we define also the magnetic field magnitude of the sunspots. So to reproduce this, if we have these sunspots for the cycle 21, 22, 23, now I put you sunspot number cycle 24, which was pretty close what you had, cycle 25, which gives you that it will be lower than 24, and cycle 26, which will be extremely low, 70% lower than any cycles. This is what we expect. At that time, we didn't know what it is. It was reduction solar activity. It could be simple reduction. It could be Dalton minimum. It could be anything. So, but we now have this nice formula, and we decided, okay, if we have formula, it's a function of time. Put the time 2,000 years. So we put the time 1,200 years forward, 800 years backwards, and voila, what we got. We predicted solar activity. First of all, we managed to predict solar activity for 2,000 years. It is published in Nature Scientific Reports in 2015. These are the data I shown with the oval, the data which we use for observations. And these are data now our summary curve obtained from that formula, which we feed, shown you with the solar activity number. But as I said, instead of being scalar vector solar activity index, our new solar activity index has polarity of magnetic field, because it gives northern or southern polarity depending where it is above or below zero in this case. What turned out, absolutely surprisingly, that indeed we are approaching to the minimum, but it is not a unique minimum. It turned out that we had previously similar minimum, which was Maunder minimum, and we had before this another minimum, which is Oort minimum, and we will have another few minima every 350 or 400 years. So there is a grand solar cycle which is defined by the interference of these two waves, two magnetic waves, defined by the sources in different layers of magnetic field, different layers inside the sun. And these grand solar cycles, every time they end up with the grand solar minima. And the previous one, it was not so far away. It was grand solar minimum called Maunder minimum, which we had quite enough information from the restoration and from the historical records and others. Therefore, this was a very important discovery. We reported this paper and this result first at the National Astronomy meeting in Llandudno in 2015. It was covered by media on many newspapers. I give just a few examples. And also we gave a few presentations. If you can follow with these links, you can find them. What basically we did, we restored then this summary curve inspired by this nice discovery. We restored the summary curve backwards up to 3,000 years and to 1,000 before Christ. So we see the blue line shows our summary curve, And the red line shows the restoration from solar radiance. And here is Maunder minimum, here is Wolf minimum, here is Oort minimum, even Homeric minimum, which happened in about 750 before Christ, we hit it. So obviously it works. There are some discrepancy that we didn't have so-called spur minimum, but we believe it was caused by explosion of supernova Vela Junior, which increased dramatically the background of the Earth's radiation. And then when people do restoration, they use standard background while they needed to use high one. This is why it is not real minimum. It was the minimum caused by supernova. So anyway, I'll hear the comparison. My time is running out. I'll move quicker. Here, just to prove you very briefly that comparison of the visual data, observation of sunspots put on our observation. This is the previous cycle from 1230 to 1630, before Maunder minimum. And you can see that the period which was Spur minimum, it was, main observers were in China, but at that time they had period of severe disease in China, possibly caused by explosion of supernova and the building the Great Wall. So this explains you, but it's good correspondent. Red spots, these are sunspots observed visually, and they fit very well in our curve. So what we've done also in this paper, we reproduced our observational result with the dynamo model, and Elena Popova helped us enormously. And it turned out that indeed, when you have this principal component and single waves, you can now reproduce pretty closely the waves. So the bottom is our observable line from magnetic field, and the top is the simulated dynamo wave of poloidal field, background field. We have also toroidal field, which is published in the paper, if anyone interested. Therefore, what it gives you, if you have real waves, it is much easier interpreted because they are much simpler. They're simple, you can apply simple formula and then reproduce this way. So this is very encouraging, especially we compare butterfly diagram for Maunder minimum. You can see this maximum 1720, 1710. We also have 1710, 1720, which close to what was observed. And how will be working this with the modern ground solar minimum? So at the bottom is butterfly diagram for ground solar minimum, Maunder minimum, and this is the current one. We remember that Maunder minimum had 6 solar cycles when the sun solar activity was non-existent. This upcoming ground solar minimum has only 3. So you see that the much brighter butterfly diagram. So it will be probably not as dramatic effect on the Earth reduction of the solar activity, but it still will exist. But what was the effect? The effect was through the solar radiance. This was originally thought. So this is on the left-hand side, the solar radiance by Lin et al. From 1995. So this is the period of Maunder minimum in here, when the solar radiance dropped from 1366 to 1363 watt per square meter. Just only 3 watt per square meter, but it gave, as you see on the right-hand side, there's a temperature variation on the Earth restored from that period. This variation, reduction of solar radiance by 3 watt per square meter gave reduction of the temperature up to 1 degree. It is in England, in Northern, and in Europe. And then after Maunder minimum, solar radiance started increasing, and so does the temperature, also interrupted, as you see, with the reduction of the temperature of a Dalton minimum, And other minimum, this is Lisbon cycle, 100-year cycle. Every century we have this reduction of the temperature. So definitely this reduction, if this happened in Mount de Minimum, and we now know that Mount de Minimum was not unique, it was standard ground solar minimum, so probably we would expect similar reduction of the temperature on the Earth during the modern ground solar minimum. Schindel et al. In 2001, they published the result showing that how the temperature reduction, temperature was during Mount de Minimum, the whole Earth, because the previous results were only in Northern Europe. And here, whole Earth, and you see that the temperature reduction actually was in most of course is in the Europe and Northern Hemisphere, but it was affecting all the other part of the planet. The surface temperature of Earth was reduced all over the globe. Europe and North America went into deep freeze. Alpine glaciers expanded over valley farmland. Ice started scratching south from the Arctic, and Danube and Thames River and canals in Netherlands froze regularly. This was because 6 cycles of minimum solar activity. Drop of temperature was related to the dropped abundances of ozone created by solar ultraviolet light in the stratosphere. So the layer of ozone is the layer in atmosphere about 10-50 kilometers of the sun, of the Earth surface. And what happened, less ozone would affect planetary waves. So why having less radiation would affect it? It create planetary waves, which basically what they do cause giant wiggles in jet streams. So all our temperature, all our radiation is actually defined by these huge jet streams shown on the left. So there is a stable jet stream on somewhat straight path. And then when you have reduction or change of ozone layer, we have wavier jet streams. And ozone layer variation would change these jets so much, they shown that it kicked North Atlantic oscillation, the balance between a permanent low pressure system near Greenland and permanent high pressure system in its south, into negative phase. And this led to Europe to remain unusually cold during Mount de Minimum. So possibly if this could happen in the previous grand solar minimum, it could happen in this one. So we need to be prepared. So what happening with the modern grand solar minimum? I nearly finished. I know that I'm running late. Just a minute. What happened with modern grand minimum? So even in the beginning, when it started 2000, summer last year, 2019, it was snow in Carpathian Mountains in July. This is the start of grand solar minimum. So January snow and frost, -2 degrees, was recorded in Amman, Arabia, first in 150 years in January 2020. Now we have in September 2020, early snow in Canada, September, and summer snow south in Australia. Again, like in Ukraine, this sea ice thickness, contrary to prediction that it will completely melt, the sea thickness in Greenland increased in 2018 and continues to grow. This is the unprecedented winter storms hit British Columbia, and now NOAA and NASA agree that it is full-blown ground solar minimum started, and the 25th cycle will be the weakest in the 200 years. But as you know from the graph I shown, just wait for the cycle 26, then it will be even weaker. So given the fact that the Earth is occurring in the solar planetary system, so solar magnetic field affects the Earth through this rotation with magnetic field and protects actually solar system from any strangers and any cosmic rays from galaxies and so on. But when during the solar magnetic minimum, this magnetic field is declined, and we now know that in modern ground solar minimum, it declined to 4 nanotesla from normal 8 nanotesla already. So decrease of solar interplanetary magnetic field would lead to increase to galactic and extragalactic cosmic rays, formation of high clouds, terrestrial atmosphere, which will assist to atmosphere cooling and will causes an increase of volcanic and earthquake activities of the sun, of the Earth. So there are two effects of the ground solar minimum through the reduction of radiation and through decrease of solar magnetic field, which both are complementary and both will contribute that we will have reduction of temperature independently of global warming and anything. It cannot override the effect of this reduction of solar activity. And I will skip this bit if we need, and we jump straight to the conclusions that we presented new proxy of solar activity principal components. We shown that with the principal component, we managed to predict the solar activity on the millennium scale and discovered these ground solar cycles. The main conclusions from, or main takeaway from this prediction was discovery of this ground solar minima, which was approaching, and we are with you in the front row observing this ground solar minimum for the next 30 years. We cannot go anywhere from it. If you want to see the materials which I presented, you can look at the website presented in here. But the main problem with this reduction of the temperature, we need to discover pros and cons of variation of the solar activity. It's very important scientifically. We understand the mechanism, how the solar dynamo works. But very practically for the people, we will be actually affected that the temperature will not have enough solar radiation. The temperature drop down, cold winter and summers, and what it will lead basically to reduction of vegetation periods. So cold winter is fine, but if winter expands to the spring and comes to the summer, it means that our vegetables, fruits cannot grow up or will not have enough period for vegetation, and therefore it will be problem with the food and supplies. So this needs for the next 30 years, indeed, intergovernment efforts to avoid the disasters. Thank you very much.